All right, y'all. So today we're going to do the rate, SL, and HL test. I'm starting with the SL material, and at the end, I'll go back to do the HL material. So, with that said, let's start with number one of the SL section. What changes would increase the rate of exothermic reaction? Now, rate is always dependent on one thing, definitely, which is temperature. And so we're looking for an increase in temperature because particles will be moving faster. And when particles move faster, they're more likely to collide with enough activation energy. You can kind of think of it like we think of the Maxwell-Boltzmann distribution. If we think of the Maxwell-Boltzmann distribution, as we increase energy, a greater proportion of reactants will have enough energy. So an increase in temperature will always increase rate. Now, next we go to particle size. When we decrease particle size, we're increasing the surface area to volume of the thing. So, for example, an antacid tablet broken into two pieces would have so much more reaction surface area that we've added right along this little break. And so decreasing the particle size also increases rate. So our answer is A. All right, for number two, which will increase the rate of reaction between calcium carbonate and hydrochloric acid? So again, an increase in temperature is always going to be good. An increase in concentration, that's adding more of the chemical. And then three is the opposite of what we said in number one. We don't want an increase, we want a decrease. So it's again A, only one and two. Number three, which conditions are required for the reaction between two molecules? Well, they need to actually collide. Their energy has to be equal to or above the activation energy. And it does, in fact, have to have proper orientation. So for that, number three is going to be D. Number four, which is the activation energy of the reverse reaction? Well, forward is this way, from reactants to products. And our activation energy is always from where we start to the peak. So you would think B, but if we're going reverse, our new starting point is D. So D all the way up to our max is going to be C. Our answer for number four will be C. Number five, several reactions of calcium carbonate with dilute hydrochloric acid are carried out at the same temperature. Which reaction has the greatest rate? So first off, we always want more particles. So higher and higher, either A or D. And now this is surface area. Surface area is kind of the opposite of particle size, kind of like what we said with an antacid tablet earlier, where a greater surface area is made by a smaller particle size. So we do want a lot of surface area. So we want large surface area. So once again, we have an answer that is going to be A for this one. All right, number six. Samples of sodium carbonate powder were reacted with separate samples of excess hydrochloric acid. And we have our reaction here. What is the same for reactions one and two? So what is the same between these reactions? Well, let's look at a couple things. Even though both are in excess, we have a much higher concentration of HCl. So this higher concentration is going to mean that reaction two is faster. So the initial rate cannot be the same. The reaction time cannot be the same. The rate of production of CO2 cannot be the same. Because we know reaction two is faster because we start with a more concentrated solution, A, C, and D cannot be the same. Total mass of CO2 will be the same. That's because we start with the same amount of limiting reactant, and the rest is excess. It's just reaction two is going to produce it way faster. Seven, what what decreases the activation energy of a reaction? Well, we literally have a saying that I wanted you all to learn forever. It's a catalyst because a catalyst provides an alternate pathway for reaction, therefore decreasing activation energy. That is the most important thing to remember about a catalyst. Number eight. Which change increases the rate of formation of hydrogen when zinc reacts with excess hydrochloric acid, assuming all other conditions remain the same? All right, so let's see. If we add water, we're diluting it, which is the opposite of concentration. So it cannot be A. All right. If we decrease the temperature, that slows the molecules down. Can't do that. If we increase the volume of hydrochloric acid, that's not actually telling us how they're increasing the volume. It could be via dilution or it could just be adding more of the same, adding more of same, which still doesn't increase the concentration. So by process of elimination, it must be D, but let's check. Decreasing the size of the zinc particles. Yeah, that's reducing particle size while keeping total mass the same. The only way we can do that is by increasing surface area. That's going to lead to more collisions. All right, number 9. Which statements are correct? So the activation energy of a reaction is not affected by temperature. Yeah, we know that's true because when we look at our Maxwell-Boltzmann distribution, doesn't matter what the temperature is, the activation energy always remains the same. So that's got to be true. A catalyst reduces the enthalpy change of reaction. Well, when we look at a reaction progress, here's our normal reaction. And then here's our reaction on catalyst. You'll notice that the overall enthalpy change, delta H, is the same. Catalysts only reduce our activation energy. So 2 cannot be correct. All right. Process of elimination already. The answer has to be B because it has to include 1 and something else. Therefore, it must be 3 because we don't have a 1 only. But let's check. Catalysts provide an alternate reaction pathway. I think I remember seeing that somewhere before. So they do. All right. 10. Which factors affect the rate of the reaction? We know particle size does because we've been talking about it over and over because that's surface area. We know concentration does because concentration of a reaction has how many particles are existing. Now, pressure of reacting gas, that does. The pressure tells you how fast they're going to be moving and how compacted they are. Remember, pressure is this idea of a lot of particles in a little space. And so that's going to have a higher pressure is going to have more collisions, while a lower pressure will have less. And therefore, our answer must be D. All right, moving on. 11. This diagram shows the energy profile for a catalyzed and uncatalyzed reaction, which represents the enthalpy change, delta H, and the activation energy, EA, for the catalyzed reaction. So, regardless, from our beginning to our end, that is our enthalpy change. Our enthalpy change is Z. So it's got to be either A or B. It cannot be minus Z because that's the reverse. And it can't be Z plus X. All right. So, and then we need the activation energy, EA, for the catalyzed reaction. The activation energy for the catalyzed reaction is going to be following this line right here. So we need this to this. So that's going to be Z plus X. Therefore, our answer must be A, X plus Z. 12. Copper catalyzes the reaction between zinc and dilute sulfuric acid. Why does copper affect this reaction? So, let's see. If it catalyzes the reaction, then we know that it must be affecting the activation energy. Erase my little mistake there. So it's got to decrease the activation energy if it's speeding it up. All right, 100 centimeters cubed of 10% hydrogen peroxide decomposes at 298 to form water and oxygen. Awesome. That is represented by this dotted line. The dotted, which represents the decomposition of an equal volume of 20%. That is twice the concentration. That is two times the particles. Therefore, we need to make 2 times the amount of O2. Therefore, our answer must be A. It's the only one that makes twice the amount. So we make 2x oxygen. 14. This is our long answer one, multiple parts to it. A student investigated how the type of acid in deposition affects limestone, a building material mainly composed of calcium carbonate. So basically, how does acid rain affect limestone? We notice that it is composed mostly of calcium carbonate, which is insoluble, bit of calcium nitrate. Then we know that calcium nitrate is soluble and calcium sulfate is also a little soluble. So those are going to come in handy when we're talking about this. The student monitored the mass of 6 similarly sized pieces of limestone. 3 were placed in beakers containing 200 centimeters cubed of 0.1 molar nitric acid, and the other 3 were in 200 centimeters cubed of 0.1 molar sulfuric acid. All right. So the limestone was removed from the acid, washed, dried with paper towel, weighed every day at the same time, and then replaced in the beakers. The student plotted the mass of one of the pieces of limestone placed in nitric acid against time. All right, draw the line of best fit. Line of best fit just tries to go through all the points. And you got to have a nice curvy line that looks like it's going close to or hitting the points. They don't have to be connected. They definitely cannot be a straight line. Straight line. This is not a line of best fit. This is a line graph. They do not want that. That's a no-no. So let's get rid of that. And actually, I'm going to use a highlighter just so y'all can see things a bit better. Pardon my barely curvy line. All right, determine the initial rate of reaction of limestone with nitric acid from the graph. Show your work on the graph and include units of initial rate. All right, so what we need to do for this is draw a tangent line from our starting point. Oh, you know what? For this graph, thinking about it, I really should draw a real line graph. That way I have something nice to work from. All right. So I'm going to go ahead and take my tangent line. Just adjust it till it's right tangent with our starting point. That looks pretty good. All right. So I'm going to take a tangent line to our time equals 0. That gives me my initial rate. Now, it's going to be sloped, so it's going to be rise over run. So if I look at my initial rate, I notice that I'm going to take the 2 points of intersection, which are right there and there. So rate is change over time. So I go from 0 to 1 seconds. So I'm going to do the endpoint. And I also notice that between that, I'm at about 47.94 minus 48.08. That is going to represent my change over time. So as I do this, I'm going to get just a moment to do math. So after a little calculation, I get an answer of 0.14 over 1. This is negative, but we're looking for change, so I'm just going to absolute value it. And something else to note is I'm going to keep track of my units. I have grams and days. So this is going to be gram per day. So I have an answer of 0.14 grams per day. So you get a couple points. You get 1 mark for the tangent line, you get 1 mark for the answer, and you get 1 mark for the units. So with that, there are your answers. The IB accepts a range anywhere of 0.13 all the way to 0.20 grams per day. So they're pretty lenient about how and where you draw your tangent line. It just has to be obvious that you are, in fact, drawing a tangent line. All right, moving to C. Explain why the rate of reaction of limestone with nitric acid decreases and reaches zero over the past 5 days. So there's a couple ways to get points here, but basically you need to first note a few things. One, that the acid's being used. Acid is being used up. That's 1 point because you'll notice that as we use up acid, the reaction is slower. Furthermore, if the acid's being used up, the concentration of acid decreases. So those will work. There's some alternate answers that you can also use. You can say acid is limiting reactant. You could also imply that the collisions are less frequent. Either way, you need one from the top two and one from the bottom two. All right, suggest a source of air, which there are so many sources of air. Um, First off, you could have non-uniform surface area. Rocks are all different, so you could have a non-uniform surface area of the rocks. You could say you have impure acid. Impure acid. So you may think that it's 0.100 molar, but it might not be. Um, you'll notice right at the top it says limestone is mainly composed of calcium carbonate. Your samples could have different compositions, so variation in limestone sample composition. Um, there could be a absorption of water. The stone can soak up some water, which would lead to incorrect mass. Because then you're not just measuring the mass. In addition to incorrect mass, you could have paper towel stuck to the limestone, stuck to stone, because they said they dried it off with paper towel when the best way to dry it is by letting it dry naturally. Um, you could have evaporation on beakers. Now that would leave your solution with a slightly more concentrated um, acid solution. You could have uncontrolled temperature, uncontrolled temp. So what if some of the beakers had some rays of sunlight hitting it, slightly warming them, speeding up the reaction? There's so many problems. All right. The student hypothesized that sulfuric acid would cause a larger mass loss than nitric acid. Justify it. Well, nitric acid is HNO3. Sulfuric acid is H2SO4. Look at that. You got two protons, two hydrogens. H2SO4 is what we call diprotic. And therefore it might be it would be more acidic. It would have more hydrogen ions to contribute to the chemical reaction between itself and the calcium carbonate. So that would be a proper justification. With that done, we're done with SL, and we're going to go all the way back to the top and go back to the HL. So starting from the top, HL data, HL test. Data is given for the reaction of 2x2 gaseous plus y2 gaseous reacts to form 2x2y. What rate equation can be inferred from the data? So let's look at x first. So what we're going to do is look at where y does not change and only x changes. So x is doubled, but the rate is quadrupled. So I know from that we have a concentration of x to the squared power. So that leaves only C and D as possible answers. All right. Now we want to look at y. So if we're looking at y, we want to see where x is the same and y changes. Y is halved, but the rate is nothing, times 1. Therefore, we know that y doesn't have an effect. Y is to the 0th order, x is to the 2nd order. We know our rate equation is C. All right, moving on to number 2. What is the activation energy according to the following plot of the linear form of the Arrhenius equation? Now, in this, we know that our activation energy, our activation energy for the Arrhenius equation is the slope of the line. So as we answer this, we can just set our EA, and we see that it will be 2 times 8.31 divided by 0.06. Our answer is A. So just to work out this problem, if we look at our slope is based on our activation energy. Specifically, it is negative activation energy over, not over K, over R, our gas constant. So when we rearrange this equation, we find that our activation energy, EA, is equal to our negative slope negative slope, not divided by R, times R. And so we know our slope is rise over run. So it's negative 2 over our run, 0.06 times our gas constant, 8.31. So just for a little extra working it out, we always have to remember that our slope is just equal to negative EA over R. I keep switching between capital A and lowercase a for that one. All right, number 3. What is correct about the rate of disappearance of nitrogen monoxide in this reaction? So as we look at this reaction, we have to consider quite a few things. We have our rate, but our rate is for the whole equation, the whole chemical reaction. If we're looking at the rate of disappearance of just NO, we can compare it to other things. It equals half the rate of disappearance of H2. Well, looking at this equation, I should be zoomed back in, pardon me, I notice a couple things. The coefficients of NO and H2 are the same. So that means every time a molecule of NO is used, a molecule of H2 is used. That's a 1-to-1 ratio. So it equals half the rate of disappearance of H2. It equals the rate of disappearance of H2. Oh, yeah, that's right there. It equals the rate of disappearance because based on this chemical reaction, this balanced chemical reaction, they should be leaving the solution at the same time. Okay, which factor influences the value of the pre-exponential factor A in the Arrhenius equation? Now, this is just something that we have to memorize what A is representing, but A represents the nature of our reactants. So 4 is A. As we go through this, we have to know that A, the Arrhenius factor, takes into account the frequency and orientation of the collisions. So for those orientation, we have to understand about these reactants. It has nothing to do with temperature, and you'll notice that because it's separate from temperature. It, again, has nothing to do with activation energy. It is separate from activation energy. In order of reaction, we notice only from experimental values. So by process of elimination, it must actually be A, even if you don't remember it. All right, number 5. Which graph shows a first order reaction? And we have these 4 wonderful graphs as shown. So we have to look at a couple things. You'll notice that these 2 graphs on the side are rate of reaction, and these 2 versus reaction concentration. These 2 graphs are reaction concentration versus time. So which graph shows a first order reaction? Well, we know that in a first order reaction, our rate constant K is dependent on the rate to a first power, and our reaction concentration should be steadily decreasing with time. It's not a linear relationship. So for this one, it must in fact be A. A couple things just to note in general. If we're just going by process of elimination, we can do that too. we know from our graphs, as we use our reactant, the concentration of it will decrease, but it decreases slower and slower because we're using it up and therefore the rate is slowing down. So that's why it can't be C. Our rate cannot increase either, not in this exponential scale, because that would represent a second order, and D would represent a zeroth order. So it can't be B or D. By process of elimination, it must be A. All right, moving on to number 6. The rate equation, rate equals K, concentration A times concentration B. Which mechanism is consistent with this rate equation? So this one's a little bit tough, but if we go through it step by step, we can first figure this out. So the first and foremost, we base our rate based on the slowest step. So I'm going to go ahead and highlight the slowest steps, and we'll go through each one. So in this case, our rate our rate would be equal to K B I. However, I represents this intermediate, and I can actually be replaced in this equation by A to the second, because I comes from the fast equation. So it cannot be A. This next one, same idea, rate is equal to K A I. But once again, I is actually based on A B. Therefore, we can simplify it to A squared. And I'm just losing K at this point. Don't worry about it. It should still be there. So much like A, B is also wrong. All right, C. Our slow is now our first reaction. So rate is equal to K A. And that's it. Just K of A. There is no other reactant. So it can't be C. Therefore, it must be D, but let's go ahead and confirm it. Rate is equal to K, concentration of A, concentration of I, and therefore concentration of I actually comes from B, so it's K, A, B. So it's got to be D. That's exactly what we're looking for. All right, number 7. A reaction proceeds by the following mechanism. Step 1, A plus A make B. Step 2, B plus C equals D. Which rate equation is consistent with this mechanism? All right, so let's look at each one individually as we go through it. Rate is K B squared C. All right, so if K is B squared C, that means this is our slow. And B squared, this is our slow because I'm looking at C. Now, I do notice that we only have one B. It is not 2B. And B actually is A. So I would notice it should probably be A squared C if we're taking it a step back because B is an intermediate. So it's not A. All right. Again, we have rate is K, A squared B, C. All right. So once again, it has C. Therefore, step 2 would be our slow one in this version. But A squared actually comes from B. So we wouldn't have both of those. All right. C. A squared. So this one is saying we don't have B and we don't have C. Therefore, this is our slow reaction. And if that is our slow reaction, it would be A squared. Yeah, I'm down with C. C's got to be right. And lastly, DKAC. No, can't be true. Here's how you can also do it instead of doing a instead of just guessing for each one and checking it out. We can literally just create the rate equation for either. So this is where step 1 is slow. If step 1 is slow, we can just see that is clearly Ka squared. If step 2 is slow, we have two possible rate equations to write. We could say K, B, C, or we can realize that B is an intermediate and say K, A squared, C. So these should be, sorry, one highlighter. These are our two possible rate equations. Those are the only two that are consistent with the mechanism of reaction as shown. All right, moving on to number 8. What are the units for the rate constant if the rate equation is rate K A B squared? All right, so we know that rate is going to be mole decimeter cubed second first, and we know K. And so we're going to go check out A. A is mole decimeter cubed. And we know that B is going to be the same thing, mole decimeter cubed. But that one's going to be squared. Sorry, I'm cramming it in. So we know that we have to do a couple of things here to get our units correct. We know we have to divide by a second. And we also have to get rid of 2 of these, so we can just get rid of the units of B. So if we can do that, we can do that with a mole on the bottom and a decimeter cubed on the top, and we can do that with those squared. So I know that K must exhibit these units right here. So I'm going to look for a decimeter cubed squared divided by second and mole squared. So I might rewrite this because I notice that they want decimeters in the front. Decimeter to the 6, second to the -1, mole to the -2. All right, that's C right there. Our answer for that one is C. Number 9, which is correct? Units of second order rate constant and effective increasing temperature on rate constant. Well, we can figure out the units quite easily because up here was clearly a third order. So we just need one less set of mole and one less set of decimeters. So I know it's going to be decimeter cubed mole second or decimeter cubed mole second. And then effective increasing temperature on rate constant. So we have to think about this. Does the rate constant depend on temperature? So when we increase the temperature, does the rate change? And we know for a fact it does. It increases. Therefore, our answer must be B. What is the intercept on the y-axis when the graph of ln(k) is plotted against 1 over t on the x-axis? So we have our little equation right here. ln(k) equals minus EA over RT plus ln A. Based on this, this is the same as y equals mx plus b. And b is always our y-intercept. Therefore, the answer must be A, ln of our Arrhenius factor, A. Number 11, which is correct for the reaction mechanism shown below. So we can first just get our rate equation. It's going to be K equals A squared. Already, that automatically takes out quite a few answers. So it's got to be either A or D. Now the overall reaction. So I'm just going to go ahead and cancel things out. B cancels B. One of our C's cancels with one C. The other C cancels with the other C. This D cancels with D. So what I'm left with is 2A reacts to form, because I have no more reactants, E, E, and F. 2E plus F. All right, got to be D. All right, number 12. What is the order with respect to each reactant? And it's a little hard because this one got shifted. So I'm going to have to look across 2 pages, zoom out a little bit. So we see NO is squared. The order with respect to NO, we know that's got to be to the second order. So it's got to be either C or D. And order with respect to CL, CL has a coefficient of 1, so it's got to be 1. We have all this data, and you can use the data, or you can just use the coefficients. And either way works. But either way, you're going to end up with C. So moving on. 13. Compounds X and Y were mixed at the same time. Sorry, were mixed at the. Let me restart reading that. Compounds X and Y were mixed, and the time taken for a color to appear was recorded at various reactant concentrations. And we have our concentrations here. What are the orders of reaction with respect to X and Y? So again, we're going to do that thing where we just kind of look at whether or not they're changing and how they're changing. So we'll start with X. X is multiplied by a half. The rate, on the other hand, also slows by 1/2. Now, it's a little awkward to see that because it looks like the time doubles, because it does. Time is doubled, but that means the reaction is half as fast. So it puts you in this weird spot where you have to remember that change over time. If the reaction happens in a longer time, it is slower. So we know that A is first order, which therefore it must be A because X is first order. We can still confirm it. We also notice over here that this is halved, but the issue is we can't use that data because X is also changing. So we instead look at a different data set. We go from here to here, where X stays consistent. And we'll notice that Y, when it is halved, the time is times 4. So Y is second order. So it's got to be A still. 14, the rate expression for the reaction is rate equals KNO squared O2 for this reaction here. Which mechanism is not consistent with the rate expression? All right, so once again, we're doing this weird thing where we're kind of working backwards for each one. Oh, sorry, zoomed in a little bit. Assuming the first one is slow, we see that we have O2. Oh, sorry, let me redo that. We have N2O2 O2, but N2O2 actually comes from NO squared looking at this reaction here. So that is consistent. A is fine. It's only one step where it is NO squared plus O2. Of course, this one's consistent because this and this are the same. So it's got to be okay. C, we're going to work backwards again. If the top one's a slow reaction, it is NO and O2, but that doesn't come from anything. Oh, that's not correct. We need to have NO squared, but they don't have it. So our answer is C. C is not consistent. All right. 15. Hydrogen and iodine react to form hydrogen iodide in this reaction here. The following experimental data was obtained. So what we need to first do is deduce the order of reaction with respect to hydrogen. So what I'm going to do is look at a place where hydrogen changes and iodine does not, and see what happens to the reaction. So in here, hydrogen is tripled. Goes from 2.0 times 10 to the minus third to 6.0 times 10 to the minus third. And I look at the rate is also tripled. So the order in respect to hydrogen is 1. It is first order. You can just say first order. That's probably the easiest way to say it. All right, deduce the rate expression for the reaction. Well, that one's not too bad. We just go rate equals K, and we know that it's first order with respect to hydrogen, but also there's a coefficient of 1. It should be first order with respect to iodine, but also there's a coefficient of 1. But we can just confirm it if we really want to. Confirming it, we have times 2. Times 2. Yeah, it's still first order. It makes sense. Calculate the value of the rate constant stating its units. All right. So for this one, we actually have to do some math here. So what you can do is plug in any of the values that you have. So I'm going to just go ahead and start off with the first one. So I'm going to plug in, let's see, this value, and this value. So I want to find the rate constant stating its units. So I'm going to say K is equal to our rate divided by the concentration of H2 divided by the concentration of I2. And I'm going to keep my units pretty consistent. 1.2 times 10 to the minus 6, 1.2 times 10 to the minus 6, and that is moles, decimeters minus cubed, second minus 1. I'm going to divide all that by 2.0 times 10 to the minus third, 2.0 times 10 to the minus third, mole, decimeter minus third. And for iodine, 3.0 times 10 to the minus third. 3.0 times 10 to the minus third, mole, decimeter minus 3. All right, so I'm going to go ahead and cancel some units real quick. Mole, decimeter minus third, it's going to cancel with mole, decimeter minus third. Then I'm going to just go ahead and plug the rest of this into my calculator. And I should get an answer that is 0.20 mole minus 1 decimeter third second minus 1. And that will get me my points here. So moving on to the next problem. State two conditions necessary for successful collision between reactants. So first off, we know that we need an energy greater than or equal to activation energy. Doesn't just have to be greater, but it has to be greater. We already know it's having a collision, so we don't have to say they have to interact, but they must have the proper orientation. So those are our 2 points right there. All right. Moving to the last problem. Yeah, the last problem. Consider the reaction of hydrogen with solid iodide. H2 plus I2 reacts to form 2HI with a enthalpy value of 53.0 kilojoules per mole. All right. Calculate Gibbs free energy change, delta G, in kilojoules per mole with the reaction at 298 using section 1 of the data booklet. Now, it's not just section 1, we have to also find the other values, but we're using delta G equals delta H minus T delta S. So as we do this, we have to find our delta S value in the data booklet. So when we do that, we actually find out that delta S for this reaction is going to be 0.1665 kilojoules per mole, Kelvin. Now, it is normally 166.5 joules per mole Kelvin. However, you must make the conversion of dividing by 1,000 because Gibbs is going to be in kilojoules. So respecting that, we're going to go ahead and plug in our values. Delta G equals 53.0 kilojoules per mole minus our temperature of 298 times 0.1665 kilojoules per mole Kelvin. We have Kelvin on temperature. Those will cancel. And you should get a final answer of delta G being pretty close to the enthalpy at 53.0 kilojoules per mole. And that is your, or sorry, whoops, I literally didn't even plug it in yet. I just kind of looked at my delta G. Sorry, apologies. It's going to be 3.4 kilojoules per mole. Whoopsies. There you go. Delta G. It's positive. Something that tells us that this reaction is also non-spontaneous at 298 or room temperature. All right. With that done, that is the test. Have a great day.